Hi everyone, I'd like to talk a little bit about supremums. So let's start off with a theorem, and this is sometimes what you'll see as a definition actually, but let's take a look at what this says. If we have a non-empty set S of real numbers, okay, so for our purposes here, I'm going to think about the open interval from 3 to 4, so parenthesis 3 comma 4, or if you're thinking about a number line like I've drawn here, I've got open circles 3, 4. I've highlighted the set here in the picture. All right, so that's our set S. We've got a non-empty set of real numbers, might be a closed interval, might be just dots on the real number line, whatever it is. And it's bounded above. So there is some sort of upper limit of our function. It's not like our set of real numbers scoots off to infinity. It is bounded above, or it has an upper bound. And so what we say is the supremum of S equals beta such that x is less than or equal to beta for all x element of S. What that means is that beta is an upper bound. That's all it means. So, just looking at our picture here, beta could be 5, it could be 10, it could be a million. It's just that beta is an upper bound. And criteria number 2 says something else. It says that if epsilon is greater than 0, then there exists some value x naught in S such that x naught is greater than beta minus epsilon. That's a very complicated way of saying beta is the least of all possible upper bounds. So let's weed through what they mean by this notation. Okay, so I'm looking at the picture here, and there's many upper bounds like 5 or 6 or 1 million, but if I'm looking for the least upper bound of this open interval, I'm thinking that the least upper bound is going to be 4. So I've labeled that here, beta equals 4. Now, epsilon is some small little quantity, so I'm just going to make a new little marker here. So let's back off from beta. Let's go beta minus epsilon. So we're just going to back off from beta a little bit. So I'm going to put a marker here and label that epsilon. Okay, so that's our little vertical line here. Beta minus epsilon means beta backed up by a small little amount. Okay, so I've gone ahead and labeled that beta minus epsilon amount. So we've got beta minus epsilon. We're backing up from beta a little bit. And what this theorem or definition is trying to say is that always in this little region, let me draw that in there. Always in that little region, always snuggled up close to beta, there is always some value that lives in your set. I don't care what you call it. They called it x naught, so I'll try to draw that in here. There's always some element of your set. And so this idea is that epsilon could be really, really small. You could make this little backed up, vertical line very, very, very close to beta, but there's always going to be something in your set S. And so this is really getting at the idea that beta is, it's not just any old upper bound, but it's the smallest or the least of all upper bounds. It's like the tightest fitting lid you could get for this set. You can't get any lower, because if you got lower, you'd all of a sudden have elements of S that escaped. So it's the least of all upper bounds.